Assalamu alaikum. I'm very delighted to get the chance to share my work with all of you. I am Roxana Parveen. I have completed my PhD from the Department of Physics, Bangladesh University of Engineering and Technology. My topic is multiferroic composite, and it is a potential candidate for memory devices. According to Hans Smith, we can define multiferroic material. Crystal can be defined as multiferroic when two or more of the ferroic properties are united in the same phase. Here we can see a simpler diagram, and we can see that in ferroelectric material, if we apply the electric field, it will cause polarization. In case of ferromagnetic material, the magnetic field will cause magnetization, and in case of ferroelastic material, the stress will produce strain. And the coupling between ferroelectric and ferromagnetic material, it is called magnetoelectrical coupling, and the electroencephalogram uses this coupling actually. And in case of ferroelastic and ferroelectric material, this coupling is termed as electromechanical coupling, and for ferroelastic and ferromagnetic material, the coupling between two is called magnetomechanical coupling. As I made my composite using ferroelectric and ferromagnetic material, and actually we try to find out the causes of ferroelectricity and ferromagnetism, and we can see that according to Spalding, the conventional ferroelectricity is causes due to the electronic configuration, that is d-naught electron are mainly offered the conventional ferroelectricity along with the lone pair electron, and the conventional ferromagnetism is due to F electron and D electron contribution actually. These are some applications of multiferroic material, and here is ferroelectric, RAM, the solid state drives and the magnetic field detector, and they can sense extremely weak magnetic field up to 1 nanotesla. And in case of spintronic materials, what is the benefit of using composite material like multiferroic material? And if we combine semiconductor with magnetic material, then easily 4 states will generate, and so we can represent 4 bits at a time in a single phase material, and in the spintronic device this is happening. I studied 2 series of composite. One is strontium substituted barium titanate along with lithium copper cobalt zinc ferrite, and the other is calcium substituted barium titanate with lithium copper cobalt zinc ferrite. The motivation was the lithium with cobalt and zinc substitution offered higher magnetostriction and offer better magnetic properties. And the lead-free barium titanate is environment friendly and large electromechanical coupling factor with high dielectric constant and low loss characteristics. This is the procedure of my composite preparation. I think I can skip this. The objective of my work was to prepare some composite material and test different properties of each and find out the findings. I have done some theoretical work along with experimental work. Sorry. And here is the X-ray diffraction pattern, and from the pattern we actually find out the phase purity, the phase formation of material. And from the X-ray diffraction pattern, we can see that our ferromagnetic part is FD3M phase, and our ferroelectric phase was P4M structure. This is the phase identification by X-ray diffraction, and from the figure we can see that both ferrite phase and ferroelectric phase are coexist in the composite, and so we can confirm the presence of both phases in a single material. Here is the Rietveld refinement, and this method uses a least square approach to refine a theoretical line profile until it matches our calculated one, and the best fit of the experimental diffraction data is obtained because the goodness of fit value or goodness of fit index have attained their lower value, and the respective crystal structure is regarded as satisfactory. This is the crystal structure of my two phases. This is the microstructure analysis, and from the figure we can see that the particle size or the grain size is gradually increasing with the variation of x. This is the hysteresis property analysis, and you all know that the magnetic hysteresis is a key factor to determine the possible application of magnetic materials. This is the ferroelectric hysteresis loop. As we are talking that our material is multiferroic, so we have to find out both the hysteresis loop for the material at room temperature. This is the magnetoelectric effect, and this is the coupling between magnetic and electric field, and this coupling offers the tuning of magnetic property with the help of electric property. It is very interesting actually. And from the figure in the C, we can see that for x equal to 15% of lithium ferrite incorporation can yield us 287 millimole per centimeter where magnetoelectric coupling. Here is a table where we compare our value with the previous reported values, and we can see that our two series yields the much higher value than the others, and it is comparable to this value actually. And in this table, the summary of all data, and the first three parameters like average grain diameter, initial permeability, saturation, magnetization, these are increases with the increase of ferrite content. The interesting part is that here in this figure, I plot the ferroelectric and ferromagnetic hysteresis loop in a single graph, and I can say that our composite form multiferroic material. Here two phases, here you see. These are the conclusion of my work. At the novelty of my work, this material can be used as in heterostructure read-write memory devices where ferroelectric write and magnetic read operation is performed actually, and it is a potential candidate for sensing magnetic field in biomedical equipment. I am very much thankful to Department of Physics BUIT, Department of Glass and Ceramic BUIT, Atomic Energy Center Dhaka, and CASR and Ministry of Science and Technology for supporting me by giving fellowship. Thank you all.
Thank you, Rosanna Parvin. Now, the presentation of